So our next speaker is Velmurugan, and he will tell us about existence of element-wise invariant vectors in representations of symmetric groups.
Hello everyone. As he mentioned, I'm going to talk about on the existence of element-wise invariant vectors in representations of symmetric groups. And this is a joint work with Amrita P and Amritan Suprasad. So let's start with the finite group G and H be its subgroup. So by a finite group G, I mean it's a finite non-empty set with a binary operation which satisfies the four properties, namely the closure, associativity, and existence of identity and existence of inverse. And H be its subgroup, meaning the H also satisfies the same with the binary operation is the restriction of the binary operation of G to H. And a representation of a group G by I mean a pair rho comma V, where V is a finite dimensional vector space over C and rho is a group homomorphism from G to GLV, where GLV is the set of all invertible operators on V. So we are very much interested in the following subgroup called monomial subgroup. So we say that a subgroup H of G is monomial if the induced representation of the trivial representation of H to G contains all irreducibles of G as its constituents. And it's natural to ask when does this contains all irreducibles, meaning for what are all the subgroups it's going to be monomial. Can we classify those, and in particular what are all the maximal subgroups? One can easily notice that the last question actually answers the remaining two as well, just by the relation on the induction. So where to start? As we all know by Cayley's theorem, every finite group is isomorphic to a subgroup of the symmetric group Sn for some n. So it's very natural to start with the symmetric group. Before that, let me talk about a very related work of Sheila Sundaram, who considered instead of all subgroups, the subgroups which are centralizers of some permutation. She considers those specific subgroups, and she has classified what are all the centralizers which are also monomial subgroups, and those correspond to partitions mu which has at least two parts and all parts are odd and distinct. And she also calls the conjugacy classes corresponding to those partitions as global conjugacy classes. Thus she is able to characterize all global conjugacy classes of Sn, and it's actually wide open for An, meaning classifying all global conjugacy classes. So let me talk about what we have done on this symmetric group. So we have considered all cyclic subgroups of Sn, and we are going to see, we are going to try what are all the cyclic subgroups of Sn which are monomial subgroup. So we use a method of Sheila Sundaram and some induction with, let me be more precise. So we basically use this induction of C mu to Sn. This guy is greater than or equal to and then there is one more induction basically. So we basically use this identity and Sheila's method to classify all cyclic subgroups of Sn which are monomial subgroups. Thus so the following partitions, the only following partitions are correspond to the monomial not monomial subgroups, meaning the cyclic subgroups correspond to partition which is not equal to one of these are all going to be monomial. So the first one is mu, where the corresponding permutation W mu is odd permutation, and the second one is the n cycle, and the third one is the permutation correspond to the partition n minus 2 comma 2 with n greater than or equal to 5 and dot. And there are some 4 finite finite partitions. The first 3 are the only infinite family of partitions. And with this you can see almost all cyclic subgroups of the symmetric group are actually going, which are contained in AN, going to be monomial subgroup. Thus there exist many maximal monomial subgroups, but we are not still clear about what are all the maximal monomial subgroups and the combinatorial interpretation of this. And we would like to note the above theorem actually holds for AN as well. And yeah, these are all the references. The first one on the existence of tableaus with a given major modular index, that's very crucial in proving these. And the other two are the related work by Sheila Sundaram. And yeah, I used McDonald to compute many things. And the one another motivation comes from the Dipendra Prasad question, and the last one is the one which we have worked recently. Yeah, thank you.
Thanks, Velu. Yeah, any questions? I don't see any. So again, we thank Velmurugan for this nice talk.